Okay. Can you guys see my charts?
Yes.
Okay. Yeah. So the intention of this talk is about purely on applications because I'm in the industry area. I'm interested in using the Liutex to solve a real problem, but since initially the code was in the internal, I mean the in-house code, so I'm very interested in a version that has Liutex implemented in the OpenFOAM. So let's go through the procedure. So the first one is the Liutex model, but I do not want to talk too much. Basically, it's everybody is expert here. I just put it here for the completeness purpose. Okay, and yeah, so what the motivation? I just like what I said. The why we use Liutex model because in general, when we deal with the unsteady flow in industry world, and we use like things like Urans and a traditional LES or more recently use the so-called IDDS models. So each of the three models or categories has their own limitations. For example, for the Urans, it fails to resolve a large unsteady vortex structures. For example, the weak shedding vortex breakdown. For example, when I try to solve the missile things, the weak just never break up. So it will take forever to hundreds of meters that prevent me to run the real things. So we need to find something that can actually break up the vortex at a certain weak length that allow me to run the CM code. So otherwise, this problem become unresolvable. Okay, so based on the description of Liutex, because it's inherently focused on the vortex structure and it has local rotation axis and something. So I'm hoping that the Liutex SGS model can provide some kind of anisotropic behavior that can bring us a better results for by running this the special specific version of OpenFOAM that I obtained from the UTI group. Okay. Okay. The second one is about the traditional LES models. So as we know, they are all isotropic eddy viscosity models. They are rely on the velocity gradients. That's a traditional way, right? And yeah, basically they will struggle with the complex wall-bounded flow and backscatter. So what do we expect to find from Liutex model? Because the Liutex model has all those local axes or something, and I think it might have a better answer. Okay, even though the current version is just a constant Liutex magnitude version. So I don't know yet. So I'm just going to put this on a test. Okay. So and I think Liutex will have a better performance in capturing vortex dynamics and the typical kinetic energy transfer. So those two things make this Liutex model a very appealing approach. Okay. So the third one is the so-called IDDS. I recently involved this kind of calculations in hypersonic flows, and I got a lot of trouble in this so-called IDDS because this is the so-called RANS LES hybrid things. Sometimes it's very sensitive to the blending function setup, and also people said that this. I do not actually get into the detail, but the people tell me that they are prone to the grid-induced separation called the GIS. So sometimes if you do not design the transition, the mesh is not designed very well, you do not get a physically correct answer. So that's get lots of troubles. But since Liutex model is naturally designed for this smooth transition, right? So theoretically, if in the future, okay, we can build another IDDS model with blending with RANS and the Liutex SGS, it could be a much better, but a much better way to run the engineering problem, because to run a real LES, for example, when I run a missile with like hundreds of body lengths domain, it's if you run really a real LES, it's not possible. So the IDDS is one of the choice. So let's open us another opportunity that the Liutex can be applied to a real engineering problem. So I just briefly say a little bit about this OpenFOAM advantage. I don't want to say too much, but I did some things here because it's open source. It's a GPL license, so we are free to use it. We are free to modify it, free to redistribute it, as long as it stay in the open source mode, right? So this will allow the Liutex SG model being free to be used for the people who are interested in. So there's no restriction. So it will maximize its impact and adoption in the CFD world. Okay, and yeah, because we can access the source code, and we can put a lot of maybe something like user routines, and maybe some special proprietary models. So let's make people make the things very appealing to the people who do specific projects. Okay, so yeah, then I don't want to get too much because so the time limitations. So now I talk about a case. So we have several cases, but I only want to talk with this one case. Okay, this is a wall-mounted cube case. This is a classic validation case referring to Martinuzzi and Chopis data. That's very rich data. There's lots of things, lots of experimental points, data collections, and a very complicated and very complicated flow structures. So the computation domain is actually a truncated domain, because this the real testing has a very long channel and a much wider domain than this. So when I got when I look at the problem, and referencing to other people's publication, I decide to chop the domain with this kind of shape. Okay, so it's like if we non-dimensionalize the domain as with the height of the cube, we have negative 3.5 to positive 11 in the x direction, with x equals to 0 as the leading edge of the cube. Okay, yeah. So the Reynolds number is pretty high based on the cube height h. The Reynolds number is 40,000. So obviously we cannot apply the uniform flow as inflow boundary condition. So in addition, we solve another long channel, basically a 2D channel. Okay, so we got a fully developed turbulence model, use RANS method, and then we compare the things with the experimental data at the S of H is equal to negative 3.0 and negative 4.0, and also the actual OpenFOAM inflow boundary condition that with the some perturbations all matches pretty well, as I would say. So I think this is a valid inflow boundary condition for this particular problem. Okay, and yeah, this is the mesh setup. So because I do not want to spend too much time, because it's really time consuming. So initially I said maybe I'll try one case with around a 5-minute cell to see what happens. Okay, so in this setup, we have like the first point of the wall is 0.01. Of course, this is non-dimensionalized to the cube height h. Okay, and I limit the maximum element scale to the 0.25. So those are the number of points listed for this 4.8 million mesh. Okay, in addition, I have another one is 11 million cell mesh. So here I reduce the first point of the wall a little bit to 0.00375. I maintain the same the maximum element scale as 0.25. So for this 4.8 million, I have 81 points on this cube. And for this 11 million, I have 105 points on the cube. Still, I cannot afford to run the uniform mesh with this 0.0075. So the mesh resolution may still questionable, and it may not actually give the most clear advantage of Liutex model. But anyway, since everything is in the same framework, same platform, so we have a chance to compare Liutex model with other SGS models and also IDDS models that I was interested in. Okay. Okay. Before we actually go to the computational results, I want to do a little bit analyze of this problem. So typically, I mean, basically, I can categorize this flow into four major flow structures. Okay, so the first one is the primary horseshoe vortex, or we call it HSV. This is basically created upstream of the cube in this unwinged phase here. So it's formed by the incoming turbulence boundary layer separating under the strong adverse pressure gradients and the wrapping around the base of the cube. So it basically will wrapping around, keep going on downstream. Okay. And the second one, this little one, okay, this corner vortex. So this one is formed by interaction and the compression of HSV against the cube leading edge. So we have this kind of vortex, and then we compress it, and we get another one. The third one are those recirculation bubbles. Okay, so this is on top face and the side face because of the separation. I mean, after so we get a separation on the top wall and the side wall, and then it reattach on the body of this cube. The fourth one is this arc-wake vortex system. So this is located downstream of the cube and formed by reattachment of the top side shear layer on the channel flow, often appearing as a large arc-shaped vortex. So this is a very complicated flow structure, okay? And this really brings us a very difficult, very big difficult challenge, okay? So how well all this model can do, how we can solve the problem, and so is Liutex model really get a better answer, or it's just comparable to other models, and which model is relatively good at the current mesh density? Of course, if we have more time and more computer hours, we can put more mesh points, or another maybe better designed mesh. So, but at the current mesh density, what we can get? Okay, so so let's maybe too many words. I was skip that, but we go to the solutions. So the numerical solutions. The first one, I'm comparing the 4.8 million mesh with the 11 million mesh results. This is the surface oil flow path. Okay. Compare with the experimental data. They have certain similarity, but not exact. Okay, 4.8 million mesh of various 2 week. Two cores. You can see the horseshoe vortex is very weak here compared to the 11 million. mesh here. So this is much, much weaker. We have some kind of side wall bubble here, side bubble here, but I don't see this arc vortex system. I don't suppose mesh. They have something possible that they're trying to create, but not eventually not created. So this could be, yeah, some reason of the mesh. So we don't know. So but we basically this is just some observations. So at this two mesh resolutions, there is no the weak vortex system can be resolved. Okay, so now if we go to another point of view, if we go to this the symmetry plane, that's streamline comparison. Okay, this is 4.8 million cell mesh, 11 million cell mesh. Okay, so you can see it's clearly that the 4.8 million is a poorly resolved that horseshoe vortex. So it's that you get a much lower down vortex center compared to the 4.8 million. I mean 11 million. So that's 11 million. We got 1, 2, 3. So 1, 2, 3. Everything's there. So that means in the front of this cube, the Liutex method has the ability to resolve the flow structure pretty well. Okay. Then let's see. So this is this going to some real test. Okay, real test. Compare with the experimental data. The first thing is the mean velocity profile comparison. Well, this can be saying is the most easy comparison in most cases because the velocity profile typically will not change too much. So we have Liutex 11 million cell. We have whale model, Samagorinsky model, spotted Amaris IDDS, Liutex 4.8 million, and the experimental data. So at the x over h equal to negative 0.5, this is upstream. We basically they are pretty good, okay? But one may see that for this spotted Amaris IDDS, we got a much higher velocity and in the negative direction. So we will expand this later. Okay, what will happen due to this thing? And so on the edge of the cube, that's the x over h equals to 0. Everything seems to be okay, very close. Okay, and at 0.5, we got a pretty strong recirculation. More or less the same compared to the experimental data, but it looks like it's a little bit down to the wall. And at the end of the cube is 1.0. Again, all this LES resolution has a little weak recirculation bubble compared to experimental data. Well, this IDDS model has a pretty good match. Of course, the 4.8 million is very bad. You don't even have the recirculations. Okay. So this is on the upstream. On the downstream, so this is on the back of the wall. I mean, back of the cube. Okay. So this 1.5, 2.0. That's 4.0 and 8.0. So these two we will see quite a lot of difference, even though most of the solutions at this same mesh density are pretty close, okay? And the downstream, I think, is very well compared. I mean, it's still some difference, but I would consider it's very well. So this is just a very first simple test. Then we go to the renal stress, the normal renal stress profile comparison. The first one is U prime square, okay? Here, the LES model looks okay, but the IDDS is very poor. Okay, you can see IDDS almost did not develop this renal stress upstream the cube. So we will find out that due to this kind of development, the poor development, the actual horseshoe vortex is very weak, even though from the streamline plot, you can still see a bubble there, but the vortex strength is very weak. Okay, similarly here, you can see this is basically they're all pretty weak. Okay, but the thing is, they are still quite far away from the experimental data. So the peak value here is still far away from the experimental data here. So none of them match the experimental data well. Okay. Yeah, all of them. So okay. So what does that mean? Okay, so that means the turbulence development is not that strong with all those models. So do we miss anything, or it's just because a low mesh density or the numerical scheme in the OpenFOAM has too much dissipation that I do not have the detailed inspection, so I cannot answer that. But with the same numerical scheme, we actually the location before 2.0, they are pretty much the same. Of course, the downstream here, it's surprising to see that 4.0, the Liutex model has much higher renal stress intensity. Okay. Okay. So let me show something in our later investigation. Okay. Now we look at the vertical, normal renal stress comparison. Again, all models looks very similar, but again, the Liutex model have this better match on this X over H at 4.0 and this 8.0 for the downstream. It looks it's better than other models. Okay, but the upstream or the immediate downstream, they are pretty much similar, even though the wiggling is different. But the peak value, I think, is similar. But here it's slightly larger, but it's still similar. Okay. So yeah, because the vertical normal stress is vital for modeling the vertical transport and the shedding of the arc vortex. The discrepancy of which is similar to the U prime square for all models struggle to match experimental data, particularly the shape and the peak of the profile in this recirculation zone. So this may be the reason. Okay, this arc-weak vortex system was not fully resolved. Okay, so maybe I am not actually a turbulence model expert, but I'm just as a application engineer, this is my understanding. Okay, so we need somehow make this the turbulence intensity higher in order to get this kind of more detailed or more accurate vortex structure. Okay, that's just my my guess. I'm not sure if even with this, if we may make it stronger, it's actually resolve it, I still don't know. But at least we need to have some way to push the things higher. Okay. Then this is the most difficult comparison. Okay, so let's see the shear stress as many model fail on the comparison of this. So the maximum discrepancy of this Reynolds shear stress is often the most difficult metric. Okay? The results deviation from the experimental data is very sufficient, even significant. So all models fail to accurately predict the negative values. So this is all negative values here, but it's far away. Yeah, wherever. Yeah, so it's especially immediately after the Q. So it's far away. So and the failure implies that the models are incorrectly predicting the equivalence momentum transfer between the high speed outer flow and the low speed inner wake flow. So there's something because they are between this outflow, I mean the outer flow outside the wake region, and the index. So we think that there might be something we need to be introduced inside the model, because right now the model is only like a Liutex, the magnitude of Liutex. So that may not actually have much advantage over like wheels or something or some other models. So that's what I said. So Liutex model is similarly to the other models and have no clear evidence of superior performance in the prediction of shear stress profile. So basically, they are very similar. Okay, some place better. It's just, overall maybe you can see slightly better, but it's not a whole lot better. Okay. Okay, now let's put all the models together. Okay. Okay, we have the Liutex, we have the Smagorinsky's, we have wheel, and we have IDDS. Okay, people may ask why this IDDS? That's because the green type things. So this is the one I said before. This because this IDDS has the runs at the wall region. So it uses this wall function, and so the velocity and first pointer of the wall is much higher. So you will see some kind of green type things. You will see some like looks like it's a stronger what is here, but this is maybe some kind of misleading because this wall function brings some artificial things inside. It's not a real things, but all the other things, all the other LES looks very similar. Yeah. So okay. And yeah. So for this one, yeah, as I said, this if you look at this streamline, you can see everything has this vortex things. Looks very similar, but this cannot tell you what which one give you the strongest vortex. So it's just a flow pattern. The flow pattern is always very similar. So if we zoom in a little bit, okay, so we can see the OLS model host vortex are very similar. So 1, 2, 3 here. So this, but this one is different. You can see that the IDDS, we almost cannot see this the little corner vortex. Okay, but all this all this the LES will be able to see. It's very clear. Okay, and one thing, if you look at a little bit more detail, you can see that Liutex has a slightly longer recovery length, so very subtle. I mean, not maybe like a 10% or 5%, 10%. This may also means that Liutex model has slightly lower dissipation. Okay, so yeah, so which is good. Okay, and another thing is, okay, I put the same flow streamlines, but I colored with the real stress, the U prime square. Okay. Now we have a much cleaner visualization. Okay. So the Liutex model, you can see a little bit stronger things upstream, and on the top it looks slightly stronger, but it's narrower. The wheel is thicker. Okay. So the peak value may not be higher, but it's thicker. But it's IDDS, even though we have this vortex, but it's almost no this real stress here. It's very, very low value. So that means we cannot just see the flow pattern. We need to see a little bit detail at the inside of these models in order to find the actual difference. And yeah, because I don't have much time to do more post-processing. Actually, we need to find out the possibly the CF, the skin frictions, and maybe possibly if we can calculate some kind of like acoustic shading things, then this will be another testing. Okay, so we can testing the vortex shading frequency and something else. But right now we just purely, very preliminary visual comparison. Okay. Okay. So and yeah, so because this the Liutex visualization has not been implemented in OpenFOAM yet, so we only have Liutex model for the Liutex SGS models, but so then I cannot compare with other models. So I still use the traditional Q criterion to compare all the 4 models to see the difference. Okay. So this one is I use the Q criterion with the threshold 19 to 20. Okay. So there's a lot of structure here. But obviously, you can see the Liutex has a complete horseshoe vortex, and some side larger scale vortex here. It's also larger scale here, but not. But here you can see this for the Smagorinsky's model. It has a much weaker horseshoe vortex, and for this Sparta-Amaris model, Sparta-Amaris IDDS model is almost gone at this strength, at Q strength is almost gone. Okay, if we look at a higher value, okay, so you can see a little bit more clear that the Liutex and whale model, even though the whale model still have a complete structure, but it's almost break. The Liutex model is still complete, while the Smagorinsky just have partly or partially the vortex tube, and this SIDDS is completely gone. Okay. So in this visualization comparison, we still can say the Liutex model is slightly better, even though it's not a whole lot better, but it's still better. Okay. And yeah, another test. Okay, another test is this lambda 2. This is another test. It's the traditional way. Okay. So this visualization comparison is for the resolved turbulence structure. Using that the lambda 2 criterion is where the true difference between SGS model, particularly their inherent dissipations, become apparent. So you can see that this is a lot of structures that I cannot say too much, but the one obvious thing is Liutex has a much less dense structure. So I'm not sure if the Liutex SGS model has a better selections that just filled out all this small structures that it's not a dominant one. It's just temporarily appeared and it just smooth out. So only leave like the very dominant things. You can see still the dominant what is here, but in this the other SGS model, it just become very messy. Okay. So this is just some observations. Okay. Now the what's the key findings and the conclusions? So this is just from the application point of view, not the academic point of view. Okay, so the first thing is okay. Maybe we can put more mesh to rerun, but yeah, this is not my initial intention. My initial intention is like if I can use the Liutex SGS model, run at a reasonably fine mesh and get much better results compared to other SGS model. But this did not happen in this particular assessment. So I need to think about it, why this happened. Okay, or maybe this Liutex model's constant can be adjusted or something else that I need the guidance from Professor Xiaokun Liu and other members in UTA team. Okay, and okay, the mean flow results comparison is a success in my opinion. Okay, so it's a pretty good comparison. That's the other circulation bubbles and the mean flow profile and the recovering length. Everything seems fine, but the turbulence stress results is quite quite a deficiency. Okay, so all models, including Liutex, significantly underpredict the peak magnitude, no matter positive or negative maximum values. It's all underpredict. So this is something that we need to study. So this failure is likely due to the lack of resolution of primary unsteady vortex shedding mechanism, so which generates bulk of turbulent kinetic energy. So we do not translate this turbulent kinetic energy properly, so we cannot form that specific the arc vortex in this particular assessment. Okay, and what I will say about the Liutex model is that this model, this current model, okay, I think there's some other models, some other virtual model, but this particular model implemented in OpenFOAM is competitive with other models, but not demonstrably superior to other models. Okay, so those just some observations. So we can try more constant tuning or some other things to see we can make it better. But this is what I'm observing now. Okay, I'll say so. My recommendation and for this assessment is the first, of course, some final mesh. Okay, so this now is 11 million. If you can easily go to like 30-40 million. So, but we can do that for one test. But from my application world, I do not want to do that. I want a reasonable mesh that can give me a reasonable turnaround time. Okay, so but one thing I'm not sure is, if OpenFOAM can have the wall modeled LES. So if this is available, maybe we can turn on this wall modeled LES. If not, then that's another story. Okay, and I can of course try to make another mesh with better topology. I can think about it. And I know the OpenFOAM has the AMR, but it's a gradient-based AMR. I'm not sure this because Liutex is different. The Liutex, so if we want to do AMR, what kind of criterion we will use, right? So for traditional LES, they can use a gradient AMR, but for Liutex, what gradient we need to use, that I don't know. Okay, so the final thing says, based on the communication with Professor Chokun Liu and Professor Yufei, they are currently developing the vector form, that's non-eddy viscosity form of this Liutex SGS model. I don't know how soon it can be put into OpenFOAM. I cannot wait to try that to see if I can get a better solution. Okay, so that's my content for that's my talk for today. So yeah, any questions?